Hi and welcome. This is part 4 of a video playlist about the preparation of phenols. A PDF version of the slides can be found under the Community tab of my channel. In this video we'll have a look at the dehydrogenation of cyclohexenones and at cyclocondensations and cycloadditions. Although these are uncommon strategies for preparing phenols, some special substitution patterns are available this way that can be difficult to achieve with other strategies. Cyclohexenones are readily accessible by Michael addition of a ketone to an alpha-beta unsaturated aldehyde or ketone, followed by intramolecular aldol condensation. The Robinson annulation is a special case of this general synthetic principle. Cyclohexenones can be dehydrogenated to phenols with a number of different reagents, which I'll show you in a minute. Then phenols can sometimes be conveniently prepared by Diels-Alder cycloaddition of acetylenes to certain dienes. Protected pyranones, for instance, can react with alkynes in the way shown here to yield protected phenols. Also furanes can react with alkynes and yield phenols by ring cleavage of the initially formed adduct. When cyclobutenones are heated, vinyl ketenes result, which can also react with alkynes and yield phenols. Let's start with dehydrogenations. Palladium-catalyzed hydrogenations are reversible, and heating cyclohexanones with palladium on charcoal can yield phenols, without any additional oxidant. In this example, even a thioether remained intact and did not cause poisoning of the catalyst. Despite the hydrogen and the alkaline reaction conditions, no elimination of the thiophenol or reductive cleavage of carbon-sulfur bonds occurred. Another potential side reaction was aldol dimerization of the ketone. This is an example of gas-phase catalytic dehydrogenation of a cyclohexenone. Such procedures are particularly convenient for the large-scale manufacture of certain phenols. Again, the reaction was conducted with a supported palladium catalyst in the presence of hydrogen. The starting enone was prepared by Michael addition and cyclocondensation of diethyl ketone with either methylvinyl ketone or with croton aldehyde. Here, oxidative and acidic reaction conditions brought about the clean dehydrogenation of a substituted cyclohexenone. A vanadium-based soluble catalyst was used in combination with pure oxygen. Unfortunately, because of the explosive dioxane-oxygen mixture, these conditions cannot be scaled up, but perhaps the reaction also works in water or with hydrogen peroxide as oxidant. Even cyclohexenols can sometimes be dehydrogenated to phenols. Here, the starting alcohol was prepared by Diels-Alder reaction of isoprene with vinyl acetate and saponification. The Diels-Alder reaction only gave a low yield because both the diene and the dienophile were electron-rich, and such reactions almost never work well. Gas-phase dehydrogenation over a supported platinum catalyst then yielded paracresol in 50% yield. One important byproduct was probably toluene, formed by elimination of water. Halogenated cyclohexenones can often be aromatized by dehydrohalogenation with bases. Such reactions may even work when the halogen is attached to an sp2 carbon atom, because in cyclohexenones the CC double bond readily migrates to other positions. Even if elimination can only occur from an energy-rich tautomer scarcely present in the reaction mixture, a high yield of phenol can result because the elimination is irreversible. In this example, a brominated cyclohexenone was treated with an excess of dBu, and a complete dehydrobromination occurred by intermediate tautomerization to a non-conjugated allyl bromide. Bromination and dehydrobromination can also be realized in one step. Here, a cyclohexenone was brominated with copper bromide and then aromatized to a phenol by refluxing with lithium bromide in acetonitrile. Interestingly, dehydrobrominations can also occur under acidic conditions. Here, oxygen continuously regenerated copper dibromide and a complete bromination and aromatization was attained. Because phenols are easy to halogenate, care must be taken to avoid bromination of the product. Catalytic iodine and DMSO can also bring about the dehydrogenation of cyclohexenones. In this example, the reaction conditions were only slightly acidic and compatible with many other functional groups. With an excess of DMSO, however, phenols can be oxidized to catechols. Thus, again, the optimal amount of oxidant must be determined to prevent further oxidation of the product. This here is a rare example of dehydrogenation with a stoichiometric palladium acetate. This is very expensive, but for the manufacture of active pharmaceutical ingredients, such a strategy can sometimes make sense. A careful recovery and recycling of palladium is, of course, essential. Dehydrogenation in this instance proceeded at room temperature in methyl THF without the need of any acids or bases. The phenol was then desilylated with fluoride. The starting silyl-enol ether was prepared by Robinson annulation of an enamine with ethyl vinyl ketone, followed by silylation of the intermediate cyclohexenone. In this example, a substituted resorcinol was prepared by bromination and dehydrobromination of a 1,3-cyclohexane dione. Like in the examples with copper bromide, halogenation and aromatization occurred in one step, just by heating with N-bromo-caprolactam. Cyclohexane diones can be obtained by Michael addition of malonate to an alpha-beta unsaturated ketone, followed by cyclocondensation. Alkenes in combination with catalytic palladium can serve as dehydrogenating reagents, as in this example. Because the reaction was conducted in methanol with an excess of trimethyl orthoformate, a dimethyl ether was obtained. Here, the starting diketone was prepared by Michael addition of a ketone to terz-butyl crotonate, followed by base-induced cyclization. 1,3-diketones and other similarly acidic compounds can be formulated or aminomethylenated at carbon by the intermediate formed from DMF and a dehydrating reagent, like in the Wiltzmeier reaction. In this example, a rather exotic dehydrating reagent was used, dichloronitroethylene, prepared by nitration of 1,1-dichloroethylene. Final aromatization to the phenol occurred by elimination of dimethylamine. This is a further example of a Robinson annulation and elimination. A phenylsulfinyl group acted both as activating and leaving group. Elimination of a sulfenic acid yielded the target phenol. Thus, Robinson annulations, where one of the reactants carries a leaving group, can yield phenols directly. This here is another example of this strategy. The initial base-induced Michael addition yielded a product mixture with a large amount of the open-chain intermediate. The cyclocondensation was completed by heating with toluene sulfonic acid for 3 hours. In this example, an imine of cinnamic aldehyde reacted with a deprotonated 3,3-dimethyl acrylate. The authors proposed a Cope rearrangement as a potential mechanism, but in principle the observed product could also have been formed directly by Michael addition. Cyclocondensation then yielded a cyclohexenone. Isomerization of the exocyclic double bond into the ring would have caused aromatization to an aminomethyl phenol, but this did not occur here. Instead, the phenol was generated by dehydrogenation with DDQ. Another fancy but rarely used strategy is the cyclocondensation of dimethylated pentadienes with a carbonic acid derivative. Dianionic intermediates are highly energetic, difficult to generate, and tend to yield product mixtures. In this example, a large excess of terz-butyl lithium was required for the twofold bromine-lithium exchange. Addition of dibenzyl carbonate then yielded the expected phenol in 70% yield. I'll show you now some examples of Diels-Alder cycloadditions leading to phenols. Here, a substituted nitroethylene reacted with a hydroxypyrone to a bicyclic intermediate, which split off carbon dioxide by retro-Diels-Alder reaction, and then aromatized by elimination of nitrous acid. To prevent radical polymerization of the starting materials during the harsh conditions of the Diels-Alder reaction, 10% of the bulky radical scavenging phenol BHT was added. In this example, a pyrone was converted into an electron-rich 1,3-diene by acetylation of the keto group. The diene added to the electron-deficient alkyne already present in the reaction mixture. The bicyclic product then fragmented by retro-Diels-Alder reaction into an acetylated phenol and acetone. The starting pyrone was prepared by cyclization of an alkenyl ketone, as shown here. The overall sequence enabled the preparation of substituted hydroxyphthalic acid derivatives. Intramolecular Diels-Alder reactions usually proceed under milder conditions than related intermolecular cycloadditions. Here the diene tautomer of a cyclohexenone added to an electron-deficient alkyne, and the intermediate fragmented into a phenol and ethylene. Alkynes also undergo Diels-Alder reactions with furanes, as in this example. Isomerization of the initially formed adduct can yield phenols. Here a gold complex was used to increase the electrophilicity of acetylene, but the yield of phenol was only low. A much higher yield was attained in this example. Here the alkyne was activated by 2 electron-withdrawing trifluoromethyl groups, and the electron density of the furane was enhanced by an amino group. A protected 4-aminophenol was obtained in high yield, without any catalyst. This is an intramolecular version of the Diels-Alder cycloaddition of an alkyne to a furane. Again, gold catalysis activated the alkyne, and a quantitative yield of phenol resulted after 12 hours at room temperature. Vinyl ketenes are reactive dienes and do also add to alkynes. Vinyl ketenes can be generated by heating cyclobutenones, as in this example. Cycloaddition with a siloxyalkyne gave a substituted phenol directly. The required cyclobutenones can be obtained by 2+2 cycloaddition of ketenes and alkynes, as in this example. Here the vinyl ketene acylated the naphthyl group intramolecularly to yield, after saponification, a phenol with a non-quite obvious substitution pattern. Isobutyric anhydride was added to protect the phenol from acylation by the ketene, and thus to increase the yield of phenol. Closely related to the previous example is this electrocyclization, which yielded a substituted naphthyl ether. The required propagyllic ethers are accessible from cinnamic aldehydes and alkynes. This is another example of electrocyclization, this time of a magnesium ester enolate. Unfortunately, preparation of the starting alene required an expensive phosphorus ylate and gave a low yield only. One rather weird but technically relevant phenol synthesis is the pyrolysis of isophorone, the cyclocondensation product of acetone. Methane is a poor leaving group, thus the extreme reaction conditions. So what about potential side reactions? In view of the many types of reaction covered, there are of course a lot. As always, oxidative reaction conditions, like those of dehydrogenation reactions, can cause the oxidation or halogenation of phenols. Then, as shown here and in some previous examples, aryl ethers instead of phenols are sometimes obtained. Terz-butyl or benzyl ethers are easily cleaved to the target phenol, but other ethers are more difficult to dealkylate. Here are some further examples which you can also find in the description of this video. The next video of this playlist is about the oxidation of phenols leading to de-aromatization, dimerization or ring cleavage. These are potential side reactions of most phenol preparations discussed so far. See you!